Undip move forward with a new spirit and tagline, noble and valuable. This spirit must become the driving force behind all aspects of our Tridharma activities, academic, research, and community services. Noble reflects the spirit and commitment to always uphold the values of humanity.
Versi ini memiliki masa yang lebih ringan dibandingkan versi yang sebelumnya. Dan kami sertai dengan teknologi Android untuk bisa mengubah pola gerakan yang akan digunakan oleh pasien.
We are determined to become a world-class university, to be part of global epistemic community that continues to carry out reproduction of knowledge for the future of humanity.
Terkait tantangan global, keuangan yang stabil diharapkan keuangan domestik juga tetap solid.
Valuable signifies our unwavering commitment to remain connected with societal challenges.
Ini air laut, ini air dari mesin desalinasi siap minum.
We strive to consistently be a proactive agent of change, delivering solutions for the various problems of the nation.
Sebagai bentuk pengabdian kepada masyarakat, kami siap menyehatkan masyarakat dan memasyarakatkan kesehatan.
We are determined that Universitas Diponegoro will continue to strengthen its competitiveness on the international stage, fulfilling its vision as a world-class university by producing exceptional and highly skilled graduates.
University is from Indonesia, DICOM University.
With a new spirit and tagline, noble and valuable, we are confident Undip can make a meaningful contribution to local and global communities.
Undip!
Bermartabat! Bermanfaat!
Sometimes, a tiny stuff or things out of sight might turn to be main cause of every possible tragedy on Earth. Hence, a living creature should be observed for the sake of science.
Selamat datang di Fakultas Sains dan Matematika Universitas Diponegoro. Kami berkomitmen menjadi fakultas riset unggul berstandar internasional, mendukung Universitas Diponegoro bermartabat dan bermanfaat, serta mewujudkan World Class University ranking 500 dunia. dan mencetak lulusan berdaya saing global serta nilai moral dan etika yang kuat.
Accordingly, we put many scientists out, dedicated every single piece of our heart for each research. Assisted with sophisticated tools and advanced technology, no matter how complicated the situation is, it will be elaborated to bring out the solution. Compounds were studied, collected up to form a theory. Every single invention were integrated with another invention.
Melalui integrasi yang harmonis antara pendidikan, penelitian, pengabdian, dan kemahasiswaan, kami berkomitmen mencapai standar world class university dengan keunggulan yang terukur dan berkelanjutan. Kami membangun ekosistem pembelajaran yang holistik, mengintegrasikan pengembangan akademik, keterampilan soft skill, dan hard skill. Penelitian dan pengabdian kami terpusat pada pengembangan solusi inovatif yang strategis dan berkontribusi nyata bagi masyarakat seperti mengentaskan kemiskinan, memperkuat ketahanan pangan, sekaligus mencetak generasi pemimpin yang visioner, berintegritas, dan berdaya saing global.
Giving wide possibilities for new circumstances to be explored, investigating the source and resources to find out novelty, and proceeding a sequence of practicums. Cultivating collaboration, domestically as well as abroad.
Ini adalah unit produksi produk inovasi yang dihasilkan oleh Universitas Diponegoro dari Fakultas Sains dan Matematika yang berbasis teknologi plasma. Ada dua produk yang sudah dilisensikan oleh Universitas Diponegoro ke PT Dipo Teknologi, Zeta Green dan D-Ozone.
Considering the wide range of science, therefore, having strong mutual relationship with as many institutions as possible is the key for any kinds of successful research.
SEMEPSA Research Center ini terbuka lebar bagi semua pihak ya, yang ingin mengembangkan riset-riset yang muaranya kepada pengembangan aplikasi biomonitoring maupun juga pengembangan sustainable aquaculture. Kita sangat membuka lebar untuk kerjasama.
Anything impossible turned to be possible. Change something insignificant into something worthy. What was only a plan transformed to be a considerable execution. Upon every lecture, whether in the classroom or in laboratory, students were driven in unimpeded discussion.
Selama perkuliahan di sini aku ngerasa dapat banyak banget ilmu, dapat banyak banget pembelajaran, mulai dari pembelajaran di kelas bersama dosen dari sisi teorinya, tapi Tapi di sisi lain, dari sisi praktikalnya, aku juga dapat banyak banget ilmu melalui kegiatan praktikum yang menurut aku pribadi sangat baik sekali untuk menunjang aku di dunia kerja.
Ketika aku masuk ke Smart Building ini, pelayanan yang aku dapatkan sangat baik karena staf yang lain ini sangat ramah dan siap membantu apa yang kita butuhkan. Di samping itu juga fasilitasnya sangat memudahkan kita, seperti pintu yang dapat terbuka secara otomatis dan lift yang dilengkapi dengan sistem sensor. Terdapat juga ruangan yang cukup luas dan nyaman untuk mengikuti kuliah umum.
Supported with adequate facilities, the Faculty of Science and Math Diponegoro University adhere to inclusive education.
Di perpustakaan ini, aku mendapat berbagai macam fasilitas, yaitu ruang belajar yang nyaman. Selain itu juga, aku dapat dengan mudah mengakses media pembelajaran, seperti buku, jurnal, karya tulis ilmiah, yang dapat memperluas wawasan dan juga membantu aku dalam pengerjaan tugas aku.
Proof by providing enrollment for disabilities. Its students deserve the same opportunity to create their own bright future.
Dengan strategi peningkatan kualitas mahasiswa, optimalisasi fasilitas, dan pengembangan sumber daya manusia, kami menerapkan tata kelola efisien dan akuntabel didukung teknologi informasi terintegrasi untuk memperkuat keunggulan institusi. Melalui kolaborasi internasional strategis dengan universitas terkemuka dunia serta sektor industri, Fakultas Sains dan Matematika Universitas Diponegoro siap menjawab tantangan global, memberikan solusi berkelanjutan, dan berkontribusi pada masa depan Undip yang bermartabat dan bermanfaat.
We strongly believe that all the dream come true emerge from the soul that keeps vibrantly enthusiastic.
Undip move forward with a new spirit and tagline, noble and valuable. This spirit must become the driving force behind all aspects of our Tridharma activities, academic, research, and community services. Noble reflects the spirit and commitment to always uphold the values of humanity.
Versi ini memiliki masa yang lebih ringan dibandingkan versi yang sebelumnya. Dan kami sertai dengan teknologi Android untuk bisa mengubah pola gerakan yang akan digunakan oleh pasien.
We are determined to become a world-class university, to be part of global epistemic community that continues to carry out reproduction of knowledge for the future of humanity.
Terkait tantangan global, keuangan yang stabil diharapkan keuangan domestik juga tetap solid.
Valuable signifies our unwavering commitment to remain connected with societal challenges.
Ini air laut. Ini air dari mesin desalinasi siap minum.
Good afternoon, Matsubara Sensei.
Good afternoon.
Okay, we will start at 1 p.m. our local time.
Okay.
Maybe in a few 10 minutes. 10 minutes.
Okay. Thank you very much.
Hello, Matsubara Sensei. Thank you for being here.
All right. Oh, thank you very much for inviting me.
Thank you for all your support, Sensei. Maybe I will land in Osaka or maybe in Chubu. Chubu
Okay.
Airport.
Is your preparation go smoothly? Excuse me, can I try to share my screen? Okay.
Yes, please.
Okay, I will try.
Recording in progress.
Yes.
How is it?
Yeah, it's very clear. Yeah, it's
No
very
problem?
clear, Sensei.
Okay.
No problem.
Thank you very much.
Thank you very much, Sensei. Ladies and gentlemen, we will start at 1 p.m. our local
Okay.
time.
Okay, so I'll come back soon.
Yeah, we will wait for the participants.
Okay, thank you.
8 minutes more, and then we will start. Thank you very much, Sensei.
Thank you very much.
Yes, aman suaranya. Oke. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi
Good
wabarakatuh.
afternoon, all participants. Thank you for joining us in online summer course in Medical Physics 2025. And now we will continue our second session. And in this session, we are honored to have Professor Kosuke Matsubara from Kanazawa University, Japan. Before that, I want to greet Professor Kosuke. Good afternoon, Professor Matsubara.
Good afternoon, and thank you very
Okay,
much for inviting me.
How are you today, Professor?
Good.
Okay, thank you so much. And to give you a better insight into his expertise, let me first read a brief summary of his professional background and achievements. Professor Kosuke Matsubara is a professor from Faculty of Health Science, Kanazawa University, Japan. He finished his master and PhD in Kanazawa University. He has specialties in radiation science, and also he is a member of Japanese Society of Radiological Technology. He has awarded many awards, and several of them is Best Oral Presentation Award from 24 ICOM and 22nd CCOM, Professor Pradut Atakorn Memorial Lecture Award from Thai Medical PCC Society in 2024, Takeuchi Award from Japanese Society of Radiological Technology, and the Best Presentation Award in Diagnostic Imaging from Thai Medical PCC Society in 2019. Today, he will talk about the introduction to CT image quality. And before any further ado, please welcome Professor Kosuke Matsubara.
Thank you very much for your kind introduction, and good afternoon, everyone. Good morning and good evening. And it is my great pleasure to have such a great opportunity to give you a lecture about introduction to CT image quality. So I will share my screen for just a moment. Okay, so please give me about 1 hour to give you the lecture entitled Introduction to CT Image Quality. Okay, so I will start. I have no conflict of interest related to this presentation. Okay, so at first, why is evaluation of CT image quality so important? It is because CT image quality is a crucial factor, critical factor, directly affecting diagnostic accuracy and patient safety. Okay, and image quality assessment requires quantitative evaluation using various metrics. So this presentation will cover the fundamental concepts of CT image quality and introduce key evaluation methods. There are many factors, many contents that should be covered, but due to the limited of time, I will summarize some of them and show you about the concept and also how to measure them. And these are key metrics for CT image quality that I will give a lecture to you today. First one is consistency and uniformity of CT number. Second one, noise level and noise uniformity. Third one, low contrast detectability. This is related to subjective evaluation. Fourth one, contrast to noise ratio, CNR. And fifth one, noise power spectrum, NPS. Sixth, modulation transfer function, MTF. And seventh, task transfer function, TTF. And eighth, section sensitivity profile, SSP. SSP is used for evaluation of not only slice thickness, but also Z-axis MTF. And these are examples of CT image quality phantoms. Left one is the CT ACR 464 phantom, and right one is CAT-FAN 600. And in addition to these phantoms, various other phantoms are sold by different manufacturers. And there are certainly many that I am not aware of, maybe. And moreover, the calibration phantoms that come with CT scanners can also be used for certain image quality evaluation purposes. I will show you one example. This section explains how to position the CAT-FAN 600 phantom. And first, place the phantom case like this at the end of the gantry and open the box and rotate the lid 180 degrees like this. Then hang the phantom from the gantry end of the box and use the level and some screws, table height, indexing drives, and alignment lights to cover the section. And this is how the CAT-FAN 600 is positioned. And in this phantom, there are many sections. And the first section, it is named CTP404. It contains 4 wire ramps, 1, 2, 3, and 4. And in this image, X and Y symmetry of the centered ramp images indicates proper phantom alignment. So if the 4 wire ramps do not appear evenly, it means the positioning is incorrect, not correct. So in such a case, please reposition. And poor positioning can affect image quality evaluation results. So take your time and position the phantom carefully. This is a very important point. And these are test modules that contains in CAT-FAN 600. And as you can see here, the CAT-FAN has many different sections, and each section allows you to test a variety of evaluation items. And having one of these phantoms is very useful for image quality evaluation in QA and QC. So I recommend you to prepare such a phantom. And the specific type doesn't really matter. And in today's lecture, I'll be giving a general overview of CT image quality evaluation. So you'll see images of various phantoms throughout the presentation, in addition to CAT-FAN. Okay, so I will start from the first one, consistency and uniformity of CT number. The background image is not directly related to the contents, okay? This is automatically selected by the PowerPoint. Okay. And this slide shows the Hansfield scale of CT number at 120 kilovolt. As you can see, the CT numbers vary depending on the material. They also depend on the X-ray energy, that means tube voltage. But this chart shows the range of CT numbers for human tissues when scanned at 120 kilovolt. Here, water is set to 0 Hansfield unit, and air is minus 1000 Hansfield unit. And strictly speaking, the Hansfield unit of air varies with tube voltage. However, since air has a very, very low X-ray attenuation coefficient, close to 0, its Hansfield unit on the scale remains nearly constant. So it can be regarded as minus 1000 Hansfield unit. Therefore, the CT number of water is defined as 0 Hansfield unit, and that of air is defined as minus 1000 Hansfield unit. For example, air calibration, we generally perform air calibration as a daily QC procedure. And air calibration is performed to establish the baseline CT number for air, which is set at -1000 Hounsfield unit. And in order to verify accurate calibration, a scan is performed that includes both air and surrounding water. This is one of the calibration phantoms, and it has both air part and water part. And their average CT numbers are measured by placing the regions of interest, ROI, around 50 by 50 pixels on the air part and also water part like this to check the consistency of CT number for air and water. And this slide shows the uniformity, how the uniformity of CT numbers are evaluated. And use the CT image of water or equivalent material. This is a water section of the calibration phantom. And on this image, place ROIs like this, at, for example, 5 locations like this, 1 at the center and 4 at the periphery, and calculate average CT number at each location for comparison. Okay, so move on to the next part. Second one is noise level and uniformity. This slide shows the noise impact for low contrast material and high contrast material. And it is well known that noise cannot be completely separated from signals. And the impact of noise is more pronounced when detecting low contrast materials than high contrast materials. In case of high contrast material, even if the noise is observed like this, there is a clear edge, we can observe a clear edge. But in case of low contrast material, it is difficult to preserve the edge due to the existence of noise. So especially for detecting the low contrast material, the noise reduction is a very important issue. And this is a simple one, a noise level evaluation. The evaluation of noise is performed using the water section of the CT image like this. And an ROI is placed at the center of the image like this. The ROI size is not so important, but I recommend you to use about 150 by 150 pixels. And place an ROI at the center. And calculate the standard deviation of CT numbers within the ROI. And if the standard deviation is higher, that means the amount of noise is larger. If the standard deviation is smaller, that means the amount of image noise is also smaller. And this slide shows the effect of radiation dose on CT image noise. As you already know very much, radiation dose affects noise in CT images. And noise is inversely proportional to the square root of the radiation dose, like this. The horizontal axis shows the dose, CTDI volume, and vertical axis shows the SD, standard deviation of CT number. And noise is inversely proportional to the square root of the radiation dose. For example, if the CTDI volume is 10 milligray, the standard deviation is about 8. And the dose is about 5 milligray, the standard deviation is 11. So the relation is not linear, but noise is inversely proportional to the square root of the radiation dose. It is a very important relationship between radiation dose and image noise. So what happens if the reconstruction kernel is changed for CT image noise? And noise depends on the reconstruction kernel used. And high-resolution kernels enhance high-frequency noise. So even if the radiation dose is the same, 10 milligray and 10 milligray for standard kernel and high-resolution kernel, the noise level is lower in standard kernel than high-resolution kernel. High-resolution kernels emphasize noise due to their characteristic enhancement of high-frequency components. So when using the high-resolution kernel, please be careful about the increase of noise. And evaluation of noise uniformity is performed using the CT image of the water section like this, or a uniform material equivalent to water or soft tissue. And ROIs are placed at 5 locations, like the CT number uniformity, and the standard deviation of CT numbers is calculated at each location to assess noise uniformity. Okay, so let's move on to the next part, low contrast detectability, LCD. And this is one of the phantom parts for evaluating low contrast detectability. And a uniform material phantom containing embedded structures such as cylinders or spheres is used. And this is only an example. It is CTP515, a low contrast module. It is embedded in the CAT-1 600. But there are several types of phantoms that have such section, such uniform material section containing embedded structures. So you can use such phantom for evaluating the low contrast detectability LCD. And evaluation is based on the minimum visible contrast and size. For example, 1% contrast and 5 millimeter size. And like noise, the low contrast detectability is affected by the radiation dose. So LCD is affected by radiation dose. And higher contrast allows recognition of smaller minimum diameters. So if you scan the phantom by 10 milligray of CTDI volume, the low contrast detectability is also higher than that scanned with 5 milligray. So LCD is strongly affected by radiation dose. And higher contrast allows recognition of smaller minimum diameters. And so what happens if you change the kernel from standard kernel to high-resolution kernel? When switching to a high-resolution kernel, noise is also emphasized. Not only the small structures, but also noise is also emphasized. However, signal is also enhanced in such a case, so resulting in small change in low contrast detectability. So when comparing the small low contrast detectability, it is difficult to directly compare the low contrast detectability between standard kernel and high-resolution kernel. It is very difficult to subjectively evaluate the low contrast detectability. So when using the different type of reconstruction kernel, it is better to select other objective type of evaluation method. So let's move on to the next part. I will move on to the more objective evaluation method, contrast to noise ratio, CNR. And this is the definition of contrast to noise ratio, CNR. and it is used as a quantitative measure of low contrast detectability. So in the previous part, the low contrast detectability is evaluated subjectively. Subjective method was introduced, but in this method, it is used as a quantitative measurement method of low contrast detectability. And actually, there are several methods, several equations to calculate contrast to noise ratio. I think this is the most simple one, simplest one. And CNR depends on the evaluation purpose and imaging conditions. The most common approach involves dividing the absolute difference in average CT number between the region of interest in the material and the background by the standard deviation of the background. And it is divided by the standard deviation of the background. And ROI is set on the signal like this. And the ROI for background is placed near adjacent to the signal part like this. And same size of ROI should be used for this purpose. And however, more sophisticated methods also consider noise within the material ROI by incorporating the standard deviations of both the material and background. So this is only one of the methods of calculating CNR, and this is also the most simplest one. But CNR is very useful quantitative metric for evaluating the low contrast detectability. But CNR cannot be used to compare images with different sharpness. So it is not suitable for images with different sharpness. And high resolution kernels reduce CNR by increasing noise, but visibility of low contrast materials remains stable. Maybe CNR is completely different between left one and right one. Left one is scanned by 10 milligray and reconstructed with standard kernel. CNR is about 3.3. And right one scanned with the same radiation dose, 10 milligray, and reconstructed with high resolution kernel. CNR is only 0.8, very low, lower than left one. But maybe the detectability, low contrast detectability is very similar, because the noise is enhanced, but signal is also enhanced. So CNR is not a perfect metric for evaluating the low contrast detectability under the different sharpness. And also, when applying the iterative reconstruction, the problem occurs. And this table shows the CNR and region conspicuity as a 3-point scale when comparing the algorithm of FBP and iterative reconstruction IR with different dose levels. And as you can see, the CNR with FBP at 100% dose was comparable to IR at 20% dose. CNR was about 2.7 at 100% dose FBP, and 2.8 at 20% dose with iterative reconstruction. But region conspicuity declined with lower dose. So CNR was almost similar, but the region conspicuity was reduced when applying the iterative reconstruction and lower radiation dose. So why such a result was obtained? This is one of the limitations of CNR for iterative reconstruction image quality assessment. And CNR, contrast noise to noise ratio, is valid when noise is uniform. Noise is uniform and follows a Gaussian distribution, Gaussian distribution. CNR assumes uniform Gaussian noise. However, this assumption does not hold for iterative reconstruction images. And iterative reconstruction suppresses noise in a frequency and structure dependent, causing the background noise distribution to deviate from Gaussian. So this is a problem in case of iterative reconstruction when applying contrast to noise ratio. And moreover, iterative reconstruction alters the noise texture. So a simple standard deviation measurement does not adequately reflect visual detectability. Therefore, CNR is considered an inappropriate metric, not appropriate metric for image quality assessment of iterative reconstruction images. So please be careful when applying iterative reconstruction images. Recently, most CT scanner can provide the images reconstructed with iterative reconstruction. So we generally use such images, but when evaluating image quality of iterative reconstruction images, please do not use contrast noise ratio. So this is very important point. And this is a relative noise reduction map. It is called NRM. And this shows the relative noise reduction map of the iterative map of the IR image compared to the FBP image. And it can be seen that the iterative reconstruction image does not perform aggressive noise reduction near the heterogeneous material like this, and also high contrast substances like this. And there is a low contrast substance around here, but as you can see, the noise level is similar with the background. But around the high contrast medium and also heterogeneous material, the noise level is different with the background. That means the low value indicates non-aggressive noise reduction. So that means, in other words, the noise distribution of iterative reconstruction is not uniform and does not follow a Gaussian distribution. That's why contrast noise ratio is not appropriate method for evaluating the low contrast detectability. Okay, so let's move on to the next part, noise power spectrum, NPS. The explanation is getting complicated a little by little, but please follow me. Okay, so first one is the noise, the definition of noise power spectrum, and apply 2D Fourier transform. By applying 2D Fourier transform to the water phantom, this is the image of the water phantom, and then squaring the transform data. For example, 256 by 256, squaring the transformed data, we obtain the 2D power spectrum of the noise image. And this allows us to analyze noise properties in more detail. So when obtaining the noise power spectrum, a Fourier transform, a 2D Fourier transform is required. Okay, and this is an example of the NPS. And NPS is shown by the relationship between spatial frequency and NPS value. So what is a Fourier transform? This is a topic of mathematics. And the Fourier transform is a mathematical tool used to decompose a signal function, waveform, or image into its frequency components. This is one of the purposes. And second one is to analyze the frequency contents to show the amount of each frequency present. And the third one is to convert a signal from the time or spatial domain. In case of noise power spectrum, it is the spatial domain. But sometimes the data of time domain is used for the Fourier transform and convert a signal from the time or spatial domain into the frequency domain. So this is the third purpose for performing the Fourier transform. And after the Fourier transform, we can divide the low spatial frequency part and high spatial frequency part like this. And please memorize that low spatial frequency noise is coarse and rough noise. Low spatial frequency noise corresponds to coarse, rough noise. And while high spatial frequency noise corresponds to fine granular noise. So the characteristics are completely different between low spatial frequency noise and high spatial frequency noise. And differences between filter kernels can be clearly seen in the noise power spectrum results. So this is an example of the results when comparing the type of reconstruction kernel. When applying the standard kernel, the NPS values are lower than a high resolution kernel. Okay, so this is the normal results when obtaining by using the both standard kernel and high resolution kernel. And let's apply the NPS to iterative reconstruction. As I already explained, the CNR has a limitation that it cannot be applied to iterative reconstruction images. But in case of NPS, it can be applied to iterative reconstruction images. And IR algorithms can alter image texture even when the noise level measured by the standard deviation is nearly identical. This is an example of phantom images. Left one is scanned by 1.5 milligray with filtered back projection. Noise level is about 20.1 Hansfield unit. The filter kernel is the same, BR44, but the reconstruction type is different, FVP and IR. And this one is the dose level was 0.33. So dose level was very low, much lower than the FBP. And noise level is almost similar, 22.9 HU, a little bit higher than FBP, but the dose level was very, very low. So the noise level is almost similar, but image texture, as you can see, the image texture is completely different between left one and right one. So noise level alone cannot fully reflect texture differences, as you can see. But when applying NPS, the difference of the image texture clearly observed as the results of NPS. As you can see, the shape of the NPS curve was completely different between red color IR result and blue color FBP results. In a low spatial frequency part, the IR shows higher NPS values than FBP. In other words, but on the other hand, the FBP shows higher NPS values than IR as a medium spatial frequency part, and almost the same as the higher spatial frequency part between FBP and IR. So that means the image texture is different between FBP and IR, and also the NPS values are different. Characteristics of NPS is different between FBP and IR. This difference can be clearly seen when evaluating NPS. And these are clinical imaging examples using FBP and deep learning reconstruction. This is recently this type of reconstruction method is generally applied. And also IR, this is ASIR-V 40%. This is the strength of the iterative reconstruction. And ASIR-V 80%. This is stronger than the 40%. And as you can see, the noise level is completely different. And also the image texture is also different. But when applying the deep learning reconstructions, even if the strength is high, the image texture doesn't change so much when compared to FBP. And this can be proved by measuring the NPS. And these results compare the NPS among FBP, deep learning reconstruction, and IR. And from these results, although the magnitude of the NPS differs among them, the shape of NPS curves for FBP, black color, and deep learning reconstruction, red color, remains largely unchanged. Although the strength, magnitude of the NPS differs. But for iterative reconstruction, both the magnitude and shape differ significantly, as you can see. So that means the image texture is completely different between FBP and IR, especially when applying the stronger iterative reconstruction strength. Okay, so by evaluating NPS, the performance of different type of image reconstruction other than FBP can also be shown. And this is only information for you. This is a new concept. This is not so new, but a relatively new concept. And low contrast, it is called low contrast object specific CNR, CNR-LO. And the CNN analysis metric that accounts for both the size of low contrast objects and the characteristics of image noise. So in this equation, not only the subtraction of CT number, but also NPS is included in this equation. So when obtaining CNR-LO, the NPS should be measured at each spatial frequency. And the new CNN analysis metric, this is a new CNR analysis metric that corresponds to the diameter of the low contrast objects and image noise properly has been designed like this. And this is results provided by this paper, Urikura et al. And this shows the effect of dose on CNR when compared between FBP and IR. And as you can see, the FBP yielded lower CNR values compared to IR at each dose level. As you can see, the CNR is different, completely different. But when applying CNR-LO, the new concept, new metric, and compared between FBP and IR, almost the same CNR-LO was obtained at each dose level between IR and FBP. So by measuring the NPS, we can also obtain the CNR-LO, which may be a useful metric as a new for applying the IR images and also deep learning reconstruction method. Okay, so let's move on to the next part, modulation transfer function. And at first, I will introduce you about the definition of spatial resolution. This is very important one for evaluating CT image quality. And spatial resolution refers to the ability of CT to distinguish two closely spaced objects as separate and evaluated in two directions. First one is in-plane direction, slice plane. And in this section, I will explain about this in-plane spatial resolution. And another one is longitudinal, z-axis direction. So it is spatial resolution is also evaluated in longitudinal direction. But I will explain this at the later part. And high resolution crucial for detecting small regions and fine details, fine structures, and measured under noiseless conditions to isolate resolution performance. So it is important to keep the noiseless conditions to evaluating the spatial resolution. The effect of noise should not be included when evaluating the spatial resolution. So that means when measuring the MTF, modulation transfer functions, a certain amount of radiation dose is required to measure under the noiseless conditions. Completely noiseless is not possible, but we should reduce the amount of noise as low as possible to isolate resolution performance. And I will start from the subjective evaluation method. And these are examples of subjective evaluation pattern types. The left one, it is included in the cat-fan phantom. The bar pattern consists of epoxy resin and aluminum plates, like this. And the right one, the bar pattern created by air gaps within the acrylic resin. And we can evaluate the smallest values by which we can identify each part subjectively. This is the subjective evaluation method. And there are several types of subjective evaluation pattern types. This is also one of the types of phantoms. And this compared the difference of kernel. Left one is a high resolution kernel, right one is the standard kernel. And in case of high resolution kernel, we can divide each part until 0.7 millimeter. So in this result, the minimum diameter of the detection was 0.7 millimeter. It is impossible to divide each part on 0.5 and 0.4. So the results of evaluation was 0.7 millimeter. In case of standard kernel, at 0.7 millimeter, part of the structure is missing and becomes invisible, as you can see. So, and completely not visible at 0.5 and 0.4. So in such a case, the evaluation value was 1.0 millimeter. This is a very simple method, and very simple subjective method, but only results for the minimum diameter are obtained. So in addition to such subjective method, objective method should be applied. So this is called modulation transfer function. And I will show you the definition, concept of modulation transfer function. Impulse signal, this is impulse signal. It is also called the delta function. And impulse signal is mathematically known as a delta function in real space. And when Fourier transformed, the MTF, as shown in the left figure like this, is always equal to 1, regardless of the spatial frequency. Always 1, keeps 1. However, after passing through a CT system, the impulse response becomes broadened like this. So this is called the point spread function. And the Fourier transform of this broadened impulse response. Original signal is impulse, but the actual signal is like this. And the Fourier transform of this broadened impulse response yields the MTF, which reflects factors such as reduced levels caused by blurring and the relative enhancement of certain frequencies to depict fine structures. So this is our ideal system, but in an actual system, the MTF becomes like this. Okay, so when evaluating the MTF, at first we have to prepare the impulse signal. So in order to obtain impulse signal, one of the methods is to use a metallic wire with a diameter of 0.1 to 0.2 millimeter fixed inside the phantom. And it is positioned on the center or the off-center of the CT system so that it is parallel to the longitudinal direction. And the CT image is acquired. This is a CT image of the wire. So the point signal can be obtained. And this is a kind of impulse signal. And this is only information for you. If it is difficult for you to prepare a very expensive CT evaluation, image quality evaluation phantom, such a phantom can be made by yourself. This is an example of custom-made wire phantom. If you can prepare such a plastic syringe, the wire is put at the center of the syringe and filled with water and locked with cork and like this, and then placed the phantom like this to obtain the impulse signal. So in such a purpose, it is possible for us to prepare the wire phantom by ourselves. So if you don't have such a phantom, please try to make a custom-made wire phantom by yourself. And I will continue the wire method to obtain the modulation transfer function. And wire appears as a point on the CT image, and distribution represents the point spread function. And two-dimensional or one-dimensional Fourier transform is performed and normalized by zero frequency. The MTF curve can be obtained like this. And at zero spatial frequency, the MTF is 1.0. And the higher of the MTF value, the better of the spatial resolution. And lower, if it is lower, the spatial resolution is not better. So this is very simple relationship. And this figure shows the one-dimensional virtual slit technique. And by virtually scanning the wire image with a slit consists of 30 to 40 pixels, the PSF is integrated along the y-axis, y direction, effectively converts the PSF into the LSF. This is a line spread function. We should convert a point spread function to line spread function. And for this purpose, we can use such as one-dimensional virtual slit technique or two-dimensional technique, two-dimensional conversion technique. The advantage of one-dimensional virtual slit technique is it is very simple method. But it is dependent on the direction of the scanning. So if the scanning of the virtual slit, direction of virtual slit is different, there is a possibility that the results of MTF also changes. So it is better for us to obtain the LSF by using the two-dimensional method to obtain the more stable results. But the process is a little bit complicated. But maybe it is very simple when you use IndoQCT. And why MTF matters? It is beyond subjective evaluation. And even when evaluation values from a repeating pattern phantom are the same, the differences in MTF properties may still exist. This is an example. The standard kernel and high-resolution kernel. In the subjective method, the minimum size, detection size was 0.7 millimeter. The same results was obtained, but the image impression was completely different between standard kernel and high-resolution kernel, and also the MTF curves completely different, as you can see. And MTF provides quantitative spatial resolution values for each spatial frequency. So if we use a different type of reconstruction kernel, it is better to compare by using the MTF, not only the subjective methods, but also obtaining the MTF by objective method. And this is a result of comparison of MTF for different kernels, standard, rank, and BOM. And as you can see, when applying the BOM kernel, the MTF was higher than 1 at the lower frequency, spatial frequency domain. But in case of rank and standard, the MTF decreased from 1 when increasing the spatial frequency, as you can see. And this slide explains about the cycles per millimeter as a unit of spatial frequency. And cycles per millimeter is a unit of spatial frequency commonly used in imaging and signal processing. And it indicates how many repeating patterns, how many white and black repeating patterns occur within 1 millimeter of space. In other words, it measures how often a pattern, like lines or edges, repeats per millimeter. And higher cycles per millimeter mean finer detail or higher resolution. So 0.5 cycles per millimeter means 1 cycle per 2 millimeter. 1 cycle per 2 millimeter. And 1 cycles per millimeter is as it is, 1 cycle per 1 millimeter. So higher cycles per millimeter mean finer detail or higher resolution. Okay, so move on to the next part, task transfer function, TTF. And IR techniques affects noise and spatial resolution properties in a non-linear manner. And as a result, the spatial resolution for low contrast object can be degraded by iterative reconstruction, even when the spatial resolution for high contrast object remains unchanged. And therefore, the wire method, relying on high contrast materials, it is a signal, impulse signal consists of higher contrast. So this is only a situation of high contrast. So wire method relying on high contrast materials cannot capture this degradation. So this is the result of MTF with wire method when applying the different strengths of iterative reconstruction. The MTF doesn't change so much, even if the IR strength changes. So it is not appropriate to apply wire method when evaluating the MTF and applying the iterative reconstruction. So in order to solve this problem, the TTF, a task transfer function, should be applied. This slide shows the key differences of MTF and TTF. MTF, modulation transfer function, measures overall system spatial resolution by analyzing frequency response and evaluates how well image contrast is preserved at different spatial frequency. And TTF, task transfer function, assesses image performance for specific diagnostic tasks, for example, region detection, and considers object shape and contrast. Both are considered related to the task for more relevant evaluation. That's why it is called task transfer function. And one of the methods for obtaining task transfer function is circular edge method. And this method evaluates the spatial resolution of imaging systems by analyzing the edge response of a circular object. So we have to prepare a phantom that contains circular object, large circular object. And specifically, it measures the edge spread function like this, or ESF, along the circular edge, which is then used to assess the system's resolution performance. And the derivative of the assemble ESF gives the line spread function. And as the first Fourier transform of the LSF uses the object-specific MTF used for task-based assessment, and it is called task transfer function. So I will show you the example of the results when comparing comparison of TTF between FBP and IR. And the FBP-based task transfer function was consistent across different inserts like this. The TTF, MTF task equals TTF, and TTF didn't change so much in case of FBP. But in contrast, the IR-based TTF depends on the object contrast, bone, acrylic, and PE, and indicating a non-linear effect. So this is because the IR iterative reconstruction has a characteristic of non-linear manner. And notably, the TTF for bone objects was dramatically enhanced with IR. Meanwhile, the TTF for PE, polyethylene objects, remained comparable to that obtained with FBP. So IR-based TTF depended on object contrast, but FBP-based TTF was consistent across different inserts. That's why TTF is important when evaluating spatial resolution for iterative reconstruction images. So I will show you the examples of TTF among FBP, DLR, and IR for these images. Okay, and in this case, the such phantom was used for for measuring the TTF, acrylic, and soft tissue. And the resolution for intermediate contrast object is comparable to that achieved with FBP, as you can see. So when applying the iterative reconstruction or deep learning reconstruction, which has non-linear characteristic, it is important to apply TTF not MTF, but TTF for evaluating spatial resolution. Okay, so move on to the final part, section sensitivity profile. And this also means spatial resolution for longitudinal direction. And thinner slice thickness improves accurate CT number reproduction in thin objects, resulting in higher spatial resolution along the longitudinal direction. And the slice thickness shown on the system console is nominal and does not equal the effective slice thickness. So in order to obtain the accurate slice thickness, we have to measure we have to obtain the SSP, slice sensitivity profile, section sensitivity profile, to obtain the effective slice thickness. And for this purpose, there are several methods to obtain the SSP, but the most simple and accurate method, I think, is to use the bead or microdisc phantom. And the phantom made of cylindrical water or acrylic or soft tissue equivalent material containing small metal ball, beads, or micro disc, and it has a diameter of 0.1 to 0.5 millimeter, or it's encapsulated inside the phantom. It's used for this purpose. And also, we can also prepare such kind of phantom by ourselves. This is an example of custom-made bead phantom. This is a ballpoint pen, and removing the ball at the tips of the ballpoint pen, and the ball is embedded in a cylindrical plate of styrofoam to prepare the custom-made bead phantom. Of course, you can also prepare the red bead at the store or somewhere to prepare the small bead. So by such a method, we can prepare the bead phantom by ourselves. So if you don't have such a phantom, please try to create such a phantom. And the phantom axis is aligned parallel to the z-axis and scanned with helical mode like this. And images are then reconstructed at intervals less than 1/10 of the nominal slice thickness to capture gradual changes in CT numbers of the microspheres. And by plotting the CT number of the bead, this is the ROI. ROI is set to cover the whole high attenuation location. And by plotting the CT number of the beads against the table position, the longitudinal sensitivity distribution, this is the slice sensitivity profile or section sensitivity profile. It can be obtained like this. And SSP values are normalized by the maximum CT number. So the maximum value should be 1.0. And the full width at half maximum FWHM of the SSP defines the effective slice thickness. And in some cases, the spread of the SSP is also evaluated using the full width at 10th maximum FWTM, which provides additional information about the slice profile. So both FWHM and FWTM are effective for evaluating the spatial resolution along longitudinal direction. And when you obtain the SSP and applied Fourier transform, we can also obtain the longitudinal MTF like this. And the longitudinal MTF degrades as the pitch factor increases. But recently, many scanners doesn't show such a tendency. Previously, it is normal that MTF degrades as the pitch factor increases. But in a recent scanner, even if the pitch factor increases, the MTF, longitudinal MTF, doesn't degrade. So the system performance improves, I think. And those and reconstruction kernel do not affect effective longitudinal MTF. Okay. And these are MPR images of the temporal bone at thread thicknesses of 0.5 millimeter and 1.0 millimeter. And upper image was 0.5, lower image was 1.0 thread thickness. And compared to the 0.5 millimeter image, the 1 millimeter thread thickness MPR shows degraded resolution of the mastoid air cells like this. But this is only a subjective impression. So by using the objective method, we can show the difference objectively. So first method is to use the FWHM and FWTM. As you can see, the FWHM is found to be about 1.9 times wider, and the FWTM is about 2.2 times wider when compared with 0.5 millimeter. And looking at the MTF at 0.5 cycles per millimeter here, we can see that there is approximately a threefold difference at 0.6 and 0.2. In this way, the image degradation can be quantitatively evaluated by using the longitudinal MTF. Okay, so in this lecture, I gave you the key metrics for CT image qualities, 8 key metrics for CT image qualities. Other than these, there are many metrics for CT image quality, but due to the limitation of time, I will give you some of these key metrics, which are generally used for CT image quality for QA and QC. So please understand one by one and perform the CT image quality evaluation appropriately. Important point is that in a recent reconstruction method, such as iterative reconstruction or deep learning reconstruction, it is some of the methods are not appropriate for using. So when using the iterative reconstruction or deep learning reconstruction, please be careful which method we should use. Okay, so please understand the advantage and limitation of these methods one by one. And this is only information. And the topics on CT image quality evaluation covered today are also included in this ebook. The name is CT Super Basics, and for which I am one of the editors. Okay, and if you are interested, I encourage you to purchase a copy and read it. It includes not only image quality evaluation, but also start from CT scanning, CT image, reconstruction artifact, and quality management, radiation dose, acquisition parameters, contrast agent, and specific examinations related to clinical images. So if you are interested in this, please try to buy it. The price is about $24 US. Okay. Okay, so thank you very much for your kind attention.
Thank you so much. Okay, thank you so much, Professor Kosuke Matsubara, for your wonderful presentation. And we have gained many valuable insights about the introduction of CT image quality. And There are many comments about your presentation. One of them is very informative PowerPoint lectures from Mr. Meher. So before we start our discussion, I want to inform the participants to fill the attendance that if you have filled out it at the morning session, so there is nothing to do with the attendance link. So we will continue with the discussion session. The first is I want to read the question from the chat Zoom, Professor. The first is from Miss Afrah Al-Sadi. Which reconstruction better for reducing artifacts, Professor?
Just a moment. There are a lot of questions, so I cannot catch up. This
Yes.
one.
Okay, it is in the very above, Professor, which from Miss Afrah Al-Sadi. Which reconstruction better for reducing artifacts?
For reducing artifacts.
Yes.
Today, I didn't explain about the artifact, but this is a very difficult question, but I think in order to reduce the artifact, it is better to apply the standard kernel or for example, using the reconstruction method to reduce the artifact. Maybe several CT scanners have such a reconstruction method. So, but it is difficult for me to explain one by one which reconstruction kernel is better and which reconstruction kernel is not better for reducing the artifacts. So please ask the manufacturer which reconstruction kernel is better for applying this purpose. But generally speaking, it is better to use the standard kernel. Or in order to reduce the for example, in order to reduce the beam hardening artifact, it is better to apply the beam hardening correction kernel or something like this. So please ask the manufacturers for more detail. Thank you.
Okay. Thank you so much, Professor Matsubara, for the answer. I hope that will answer your question, yes, Miss Afrah. And we will continue to another question from Mr. Amir Ali. Kindly explain how air attenuation coefficient is related to tube voltage as you described during lecture.
Okay, so just a moment. Air attenuation coefficient is related to, okay. And actually the air attenuation coefficient doesn't change so much even if the X-ray energy is changed, because the air attenuation is very small, very small, and it is almost negligible. So the CT number doesn't change so much even if the tube voltage is changed.
Okay, there is the answer from the professor for the question from Mr. Amir. Another question is from Mr. Salem Salah Masabi. How do specific technical factors such as kernel selection or iterative reconstruction algorithms influence the noise power spectrum NPS in CT imaging, Prof?
Okay. It is strictly speaking, it is very complicated. And generally speaking, if we use the high resolution kernel, the NPS value increases. And if the standard kernel or soft tissue kernel is applied, the NPS value decreases. This is a simple relationship between the kernel and NPS. But recently, there are several types of kernels, and also we can apply the iterative reconstruction method. And as I already see the slides of the NDPS curves during my lecture, the shape of the NDPS curve is completely different between FBP and IR. So it is very difficult to explain the relationship between the spatial NDPS and reconstruction kernel or reconstruction method by words. But it is very complicated, I think.
Okay, thank you, Professor. Okay, before we continue, I want to invite also the offline participant. If you have any question, you can raise your hand. And also, if you want to ask directly to the Professor Kosuke Matsubara, you can also raise your hand in the Zoom. Okay, we continue the discussion with the question from Ms. Nila Prastia Aryani. Thank you, Professor Matsubara, for your very interesting presentation. I would like to ask, if we perform CT image reconstruction using both deep learning and conventional methods and aim to quantitatively assess the difference of image quality, which evaluation metrics will be most effective for this purpose?
Okay, thank you very much. And I think if we want to evaluate the noise properties and also spatial resolution, it is better to use NPS, noise power spectrum, and TTF, task transfer function. And recently, there is a new metric that take into account both the spatial resolution and noise. It is called the SNR, or such as D prime. I forgot the correct name of the D prime. Detectability index, detectability index, or system performance function. Or there are several types of new metric for evaluating the image quality for iterative reconstruction and also deep learning reconstruction. But anyway, these values consist of both NPS and TTF. So it is better to evaluate both two factors, NPS and TTF. This is my recommendation.
Okay, thank you, Professor Kosuke Matsubara, for the answer. Another question from Mr. Muhammad Yasin. First of all, thank you very much for such a nice presentation, Professor. My question is, how can I learn the basics and understand the significance of all these image quality metrics?
Thank you very much. I think this is very difficult question, but the most I think the best way is to attend this course and learn many things during this course. I think this is the most simplest way to understand about the basics and significance of these image quality metrics. Maybe from tomorrow, the lecturers will give the attendees the lectures one by one about each contents, each key metrics of CT image quality evaluation. So please continue to join this course at the end of the course and learn many things during this course.
Thank you so much, Professor. And yeah, as mentioned before by Professor Kosuke Matsubara, you can dive deeper about the CT image quality in our online summer course. So please stay tuned, since for tomorrow we will discuss more about the CT image quality, and we will also practice about how to evaluate the image quality using IndoQCT. Okay, now we will continue to another question from Mr. Mahmud Nasif. How do reconstruction kernels and flash thickness influence CT number accuracy and low contrast detectability in radiotherapy planning? And what strategies can be used to optimize both simultaneously?
Okay, just a moment, please. In case of radiotherapy planning, this is not the target of my lecture, but of course the reconstruction kernels and slice thickness influence CT number accuracy and also low contrast detectability. But it is they are the scanner dependent, I suppose. So it is better to evaluate such size thickness and low contrast detectability, including CNR and also NPS, TTF, by using the radiotherapy planning scanner and check the image quality one by one for proceeding optimization of scanning parameters for radiotherapy planning. I'm not sure whether this is a good question, a good answer or not.
Okay, I hope that will answer the question from Mr. Mahmud Nasif. And we continue to another question from Mr. Muhammad Yasin again. Could you explain what a kernel is and what is essentially means?
Okay.
Mr.
Kernel.
Mahmud Nasif also have given any opinion. Kernel is reconstruction filter, like a turning knob that decide whether you want more detail or less noise in your CT image. But if you have any additional opinion, you can give it, Professor Matsubara.
Okay. Kernel is, as he said, the kernel is reconstruction filter. Yes, yes. And it changes the characteristics for each spatial frequency, I suppose. So by applying the different filter kernel or reconstruction filter, that means in some cases the noise is enhanced. In some cases the small structure is enhanced. In some cases, but other cases the noise is reduced or something like this. It is very complicated relationship between the type of reconstruction kernel, reconstruction filter, and the image quality. But overall, I think I agree with the opinion that kernel is reconstruction filter, and also it changes the impression of images. It changes the characteristics of image for each spatial frequency.
Okay, thank you, Professor, for the answer. And we will continue to another question from the chat Zoom from Ms. Nadia Alesai. Are there any limits that can guide us during the acceptance test when performing image quality metrics? And are they mentioned in the unit's technical specification?
Thank you very much for your good question. And the limitation of CT image quality evaluation is that it is only the phantom-based evaluation. So even if the evaluation results of by using the phantom is better, it always doesn't mean that the image quality is also good for clinical use. So it is better not only evaluating based on the phantom but also the image quality should be evaluated based on the clinical images. such as by using the subjective method.
Okay, thank you so much, Professor, for the explanation. There is another question from the chat Zoom from Ms. Nurfatia Hairunisa. Thank you so much, Professor Matsubara, for your interesting presentation. I would like to ask about spatial resolution in city image QC practice. Spatial resolution testing is often performed using a bar phantom, but the results can be biased or subjective depending on the observer. How can MTF measurement be applied in city image quality QC to achieve more accurate and consistent spatial resolution assessment?
Thank you very much. And as this attendee said, that subjective evaluation is based on the observer's evaluation. So it has some kind of bias, yes. So even so, if the observer A and observer B evaluates the same image, there's a possibility that the results are completely different. So there may be some bias on subjective method depending on the observer, as he or she said. But in the method of objective evaluation methods such as MTF or TTF, such bias can be avoided because this is the objective method. So the meaning of objective method, or the advantage of objective method, is to avoid such bias, and we can obtain the results that can avoid such a bias. So by applying MTF or TTF measurement, I think the results are more accurate, and also we can avoid such bias.
Okay, I hope that answer will answer the question from Ms. Nurfatia. Yes, Ms. Nurfatia. And now another question from Ms. Yin Moy Ai. According to the slide 49, there is 3 different kernels, and could you please explain any detail of MTF changes in low spatial frequency, because MTF is higher in lower spatial frequency with one kernel?
Okay. Shall I share the slide one more time? Okay.
Oh, yeah. Yes, please.
Just a moment. I think it is about this slide, and I show the 3 examples, results of 3 MTF curves for different kernels, and one of them is a bone kernel. And as you can see, when applying the bone kernel, the MTF was above more than 1 at the lower frequency part, like this. And this is due to the undershoot of the image. And when applying the bone kernel, the undershoot is observed on the image. And this is the reason why the MTF was more than 1. But in case of long and standard, the MTF is always less than 1. But the MTF results is also different between long kernel and standard kernel. This is due to the different characteristics of these kernels. So long has power. Long kernel has the characteristics to enhance the small structure than the small standard kernel. But maybe the noise is also enhanced, so that the noise level is higher than standard kernel, I think. in this slide, there's no data about the noise, but when I also show the results of the noise, maybe the noise level is the highest at the bone kernel, and the second highest at the lung kernel, and the lowest at the standard kernel.
Okay, thank you, Professor. How about the Miss Yin Wei? Are the answer from the professor answer your question? I hope that's so. Okay. Since we also
Can I ask for a minute, Professor?
From Mr. Aris, Professor.
Okay. So as you mentioned before, in the NPS noise power spectrum, different kernel produce different texture, noise texture.
Yes.
And also different iterative level will also produce different texture. Texture is described in mean frequency or peak frequency. So in your opinion, which is better for detectability? Is it a higher frequency or a noise in the low frequency?
Oh, thank you very much for your good question. I think for the region detectability, not only the spatial resolution, but also the noise level is important. So we have to take into account both factors, noise and spatial resolution. So it is better to evaluate by taking into account both factors, including noise and also the spatial resolution, by using the index such as detectability index. And if the detectability index is higher, that means the region detectability is also high. So it is. So I think my opinion is to evaluate by using such a factor and decide objectively. Okay. Thank you very much.
Thank you very much, Sensei.
Okay, thank you very much, Mr. Arich, from your question. Now I invite the participant, since we conduct this summer course hybrid. Is there any participant from the offline that want to ask directly to Professor Kosuke Matsubara? Or another participant, maybe you can raise your hand also to ask directly to Professor. As waiting for another question, I think I want to ask question for you,
Okay.
Professor.
Okay.
Since we talk about the TTF, and the TTF is applicable for the ER reconstruction, for spatial resolution, is it okay for us if we directly measure the TTF to evaluate the spatial resolution in both FBP or ER? Since even though it influences on the FB IR only, but and there is no influence for the FBP, or is it okay for us to still use TTF for the FBP reconstruction, or for the FBP we use MTF, and for the IR we use the TTF?
Okay, thank you very much for your question, and I will share the screen one more time. I think this is the most simple one that you can understand. This is the results of the comparison of TTF between FBP and IR. And in case of FBP, even if the material, type of material changes, the results didn't change so much. This is because the characteristic of spatial resolution is not object dependent or size dependent. So even if we apply TTF for evaluating the spatial resolution, the results we can obtain the similar results with MTF. So it is, I think we don't need to use separately MTF and TTF, MTF for FBP and TTF for IR or deep learning reconstruction. There's no need to do like this. In a recent case, I recommend you to use TTF method to evaluate spatial resolution. Okay, even if we use the FBP.
Thank you so much, Professor. Another question from me. In your presentation, in the beginning, you mentioned about the city number accuracy, and you also explained about the evaluation using the square ROI. Since in Indonesia, we commonly use circular ROI. Is there any influence about the shape of ROI and which and the shape, the size, and which one is you recommended for us to use if we want to evaluate the city number?
Oh, thank you very much. Actually, that's no big effect, even if we use circular ROI. So it is also good to use circular ROI. So it depends on the environment of the scanner or the system that you use. So even if you use the circular ROI, maybe the similar results can be obtained. The important point is the size of the ROI. The size should be similar.
Okay, thank you, Professor. Maybe, is there any question still from the participant, both from the online or the offline? Is Dr. Anam, there is any comment? Okay, Dr. Anam will give any comments about your lecture. Please, Dr. Anam.
Okay, thank you, Professor Matsubara.
Thank you very much.
For a very nice presentation, and we are very helpful. And for the participants, tomorrow we will try to measure the MTF, DTF, and also D prime automatically using IndoQCT. So please attend the tomorrow until the
Next week.
next week's inshallah. We will try together how to measure MTF, NPS, D prime using IndoQCT. Okay, thank you very much, Professor Matsubara.
Thank you very much.
Okay, thank you, Professor Dr. Anam, for the comments. And maybe there is a closing statement from Professor Kosuke Matsubara about today's lecture that can give to us.
Okay, so thank you very much for joining my lecture today. So I give you the information about the key metrics for CT image quality, and they are very important, I think very important for keeping the good diagnostic accuracy. And image quality assessment requires quantitative evaluation using various metrics. So please understand how these image quality metrics can be performed, should be performed one by one. And I hope my presentation would be helpful for your understanding about the CT image quality evaluation. Thank you very much for attending my lecture today.
Thank you so much, Professor. And I will say that your presentation is very helpful and it's very interesting there, and many all of us that learn about the key metrics about the CT image quality. And thank you so much once again, Professor. And I think this is the end of our session. For the participant, I want to remind all of you that we will continue our summer course tomorrow with the topic of IndoQCT installation, IndoQCT as DICOM viewer, and also DICOM hierarchy, DICOM text, and computational phantom that will be delivered by Dr. Haidul Anam and team. Okay. For information, the Zoom will be opened at 30 minutes earlier before the course, so you can join by 9 past 30, and the lecture will be started at 10 a.m. local time. Okay, maybe it is enough. Thank you so much. Once again, Professor Kosuke Matsubara and all of you that have joining us today, and see you tomorrow with another lecture. Good afternoon. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you very much, Sensei.
Thank you very much.
Thank you very
Thank
much.
you very much, Sensei.
Thank you very much, Sensei. See you again. Bye-bye.
Bye-bye.
Bye-bye. Thank you very much.
Okay, see you tomorrow.